So hello again, everyone. So my first lecture was 48 hours ago, and since then you've had a lot of new ideas, so it may be a bit out of your mind. So let me remind you what the overall plan is for this course. So in the first lecture, I tried to give you an overview of the area. We're thinking about many body systems with a limited number of conservation laws, or in some cases, no conservation laws at all, and we're thinking about states high up in the spectrum, so there's no quasi-particle description, and we're thinking about different ways of probing dynamics in those systems. And as I explained in the overview, we might look at the dynamics of operators in the Heisenberg picture, or we might think about the evolution of states in the Schrödinger picture, in which case we might focus on entanglement in the states. Or otherwise, if we're thinking about the evolution operator or the generator of the evolution operator, the Hamiltonian, we can look at spectral properties, which turn out also to give us a diagnostic for the dynamics. And then in the lecture on Tuesday, beyond the overview, I started talking about operator dynamics in more detail, and I talked about the Lieb-Robinson bound, and also about the out-of-time order correlator. So you remember the idea was to find out whether two operators which act at different places in the system commute with each other after one of them has been evolved in time. And the idea is that if they're located at places far apart in the system, then at early times, they should still commute. And so this commutator, whose value we can probe by taking the modular squared, by which I mean the commutator times its Hermitian conjugate, and then, if we like, averaging, either or over a choice of initial states weighted by a density matrix, and then in addition, in these systems where we're thinking about ensembles, over different members of the ensemble, then looking at this quantity will tell us how much this operator, originally centered on the site X, has spread. And if we expand the commutator, we get 4 terms, and the result we can write here, as I explained. We get 2 terms of one type and 2 terms of the other type. That's this factor of 2, the q to the minus L and the trace from the quantum average. And then these terms behave rather differently. This one is quite simple. I mean, for instance, we might choose our operators to be like Pauli operators and squaring to unity. And if that's the case, well, it'll be true both before time evolution and after time evolution. So this term will be equal to 1 if the operator at x squares like the operator at y to the identity. And this other term, well, I emphasized in my first lecture that it's different from the correlators one's used to thinking about in many body theory, because the operators that appear are not in time order. And then Silvia Pappalardi, at the end of her last lecture, explained how one expects this to go to 0 at long times. So this is 0 at long times. And if we put those ideas together and think about the behavior of this correlator, then at early times, we expect these operators to commute, and so we get 0. And at late times, this term goes to 0, and this term goes to a constant, so we get this plateau. Now, well, first, I guess I should check any questions about anything there or the background leading up to it. Okay, so the thing that I want to do in the first of today's 2 lectures is to actually calculate this for random quantum circuits, and I want to go through the calculation in enough detail that I hope you'll feel you've seen all of the important ideas. And in order to do that, I need first of all to point out a few basics about thinking about operators. So the idea here is to calculate the OTOC in random unitary circuits, and basically I'm giving you the essentials of 2 papers, one by Adam Nahum and collaborators, and the other by Kurt von Keyserlingk. And they were both in 2018. So the background that I need to remind you of is that we can think about operators as elements of a vector space So let me think first of all about one side of this system that we considered when we built up the idea of a quantum circuit. So if we take a single site with what I was calling the local Hilbert space dimension, denoted by Q, then the number of linearly independent Hermitian operators is Q squared. And this is familiar to you, no doubt, in the simplest case where I just take a spin-a-half system so that Q is 2, and then we have 4 linearly independent operators, which you often take to be the 3 Pauli matrices together with the 2x2 identity. But we'll keep Q general. And if there are elements of a vector space, one of the most important ideas is a scalar product. So we'll take the scalar product between 2 operators to be the dimension of the vector space. So here Q inverse times the trace of the 2 operators. So scalar product of, well, I'll denote the 2 operators by A alpha and A beta. And so I'll take the scalar product to be the trace of the product of the operators. And I'll choose an orthonormal basis. So I'll take A alpha to be orthonormal basis. And then I have q to the minus 1 trace of A alpha, A beta being given as 1 if the operators are the same and 0 if they're different. Now, the final basic point that I want to make is that in what we're thinking about, the unit operator will play a special role. And although I, in general, might think about an orthonormal basis with all sorts of orientations, I'll take, in fact, the unit operator to be one of my basis operators. So I'll take the identity to be one member of the basis. So incidentally, that means that this orthonormality condition will tell us that all of the other operators, if they're orthogonal to the identity, they must have trace 0. And what's more, the number of operators orthogonal to the identity, it's just the total number q squared minus 1. So I'll talk about non-trivial operators. And I have q squared minus 1 of them. Okay, so I guess that's standard stuff, but it's important to have in mind. Now, yeah, thank you. No, so here I'm talking about operators that act on a single site, and the identity is one of those operators. So it's q by q, yeah. And so, I mean, that also fits with this normalization and so on. Yeah. Yes. Absolutely, yes, yes. Okay, so that's defining a scalar product and a basis at a single site. But now we need to go from the single site to operators on the whole system. And again, in principle, we could use a basis with all sorts of orientations in this space of operators, but we don't want to do that. What we want to do is take as our basis for operators in the whole system direct products of the basis operators that we've defined on the individual sites, and we're going to call these operator strings. And so if I have a particular string S, then, well, on some sites, I may simply have the identity acting. And then on some sites, I might have the non-trivial one of the non-trivial operators acting, and I guess now I'm switching notation a bit. When I write A, I mean explicitly one of these q squared minus 1 non-trivial operators, and I'll have something non-trivial here, and then I might have an identity, and then eventually I'll have some other non-trivial operator, and then, and this is the point I want to make, I may have identities all the way to the end of the system. And so one idea which is useful to keep in mind is what we can call the length of the string, which is the distance between the leftmost and the rightmost non-trivial operators. So here in this example, this would be the length of the string. And I've deliberately drawn an instance where there are some identities somewhere in the middle, and it could be that in some circumstances you'd only want to count the sites on which you have non-trivial operators acting, but for the present purposes, I want to really focus on the first and last non-trivial operators and the distance in between them. Yeah. There doesn't have to be an identity in the middle. What I want to say is we have, as you said, a bunch of identities and then something that's not the identity. And then we don't really care what's in the middle here, but eventually we get to the last thing that's not an identity, and then we have identities. In the middle is exactly whatever. Okay, so how many strings do we have? Well, these are operators on a Hilbert space of dimension q to the power L, and the number of basis operators is the square of the Hilbert space dimension. So we have q to the 2L distinct strings as the basis. And so our scalar product now is a trace, and then we can have one of these strings which I'll label S, and potentially different string which I'll label S primed. Well, this is maybe notation which is simplified too far, but still I'm going to stick with it. I'll use S both as a label and to note the string itself. And we normalize these traces with the dimension of the Hilbert space. So here the normalization will be q to the minus L. And because we've taken tensor products of basis operators that are orthonormal at each site, this is a Kronecker delta on the different strings. Okay, so is that all clear? Now, why are we doing this? Well, we want to be able to talk about operator dynamics, and so it's convenient to use this basis as a way of representing the dynamics. And so what we can say is that we'll expand the time-evolved operator that initially was a string of length 1 if it only acted at the site x, will expand that for all times in the basis of strings with expansion coefficients for each of the strings, which will clearly depend on time. That's how time goes. So these expansion coefficients and whereas you're used to expansion coefficients often being complex quantities, here, in fact, they're real, and that's pretty easy to show. And in one of my problems, that's a small part of one of the questions. Now, we can choose our normalization for the observable that we're thinking about here, but it's often convenient to do what I talked about when I was talking about the behavior of the OTOC in the introduction, and to think of something that's like a Pauli matrix, and so we'll normalize the initial operator so that if we take the trace of its square and normalize the trace in the way I'm talking about over here, we get just 1. Okay, there's some ambiguity. I mean, often if you talk about a Pauli matrix, you wouldn't think of attaching all these unit operators to it, and then you just take the trace normalized by the dimension of Hilbert space at one site. But if we attach all these unit operators at the other site, then the square of the Pauli matrix would be something with unit operators at every site, and this would be the right normalization for the trace to give us unity. So the point is that if we normalize our operators that way, or however we normalize the operators, then this is something that's preserved under time evolution. Because obviously if we think about the time evolution operators that appear here, then when we take the trace of the square, they all cancel. But now we can also think about this condition in the language that we're using here. And so what this implies is that, well, if I take the square of x of t, I've got a double sum over s and s primed, and as of t, a s primed of t, and then I've got q to the minus L trace of s primed. But this, we've already said, is a Kronecker delta. And so what this gives us is, let me what this gives us is that the sum over S prime of AS of t squared is equal to 1. As I said, these are real quantities, not complex quantities. And so what this is telling us is that these amplitudes for the operator on strings are a bit like amplitudes in a real wave function. And we can think of the operator that initially acted at a particular site as spreading over these different basis states as time goes by. So we've got a conserved density Yes.
Is there, so I'm guessing for like t equals 0, will be some constraint on locality for these operators in the coefficients A?
Right, well, that's our choice. But what I'm suggesting is that the interesting thing to do is to take the initial operator, that's to say O of x without a time argument, or O of x at time 0. The interesting thing to do is to take that to, for instance, act on a single site. So in that case, in this expansion over a sum of strings, there'll only be a single string at time 0 with non-zero expansion coefficient, and that will be the string corresponding to the initial operator. So in that sense, yes, as you say, there's locality initially. Okay, so there's a simple geometrical picture which it's worth having in mind. So if this is the system that I'm thinking of with sites like this, and suppose my initial operator acts just on this site, well, if I now draw in the gates of the random unitary circuit, then it may be that I have gates acting like this. At successive times, so this will represent the time evolution operator. And then actually, if I'm evolving an operator rather than a state, I should really think of the conjugate evolution operator acting on the other side. So I'll have conjugate gates here. And these are representing W dagger of t. And then if you think about how the operator initially localized on a site can evolve, well, the effect of these two gates here can only move the operator a certain way. It can give us some weight on this other site. And in that way, you get a kind of light cone which you can draw through the circuit as I've shown there. And rather trivially, what you can see, I hope, is that the operator OX of t has zero weight outside the cone that I've drawn, which you could call the trivial light cone or just the geometrical. No, that's the case. That's correct. But what we're going to find is that, in fact, the almost all the weight of the operator is concentrated inside a light cone which has a smaller velocity. So on this picture, these lines go up with larger slope.
Like the bottom half, I mean, like you also have W data because you're revolving an operator and not a state.
That's the idea, exactly. Yeah. Right. What I've drawn here is not the butterfly velocity, and it's something which you can see just by inspection without doing any calculations because of the nature of these quantum circuits. Just because of the geometrical properties of the quantum circuits. So that's an upper bound on any light cone velocity, but the calculation that we're about to do tells us something more interesting than that, and it gives us a velocity that's smaller than that. Okay. So the next point is that clearly, if we think about all of these strings and the associated amplitudes, we're dealing with an awful lot of information. We're finding out whether the operator is spread to something with lots of holes in it, or all sorts of things. And it's just too much information to keep track of. But fortunately, if our basic aim is to discover how long the strings are that the operator spreads into, then we can collapse that information into something that's simpler to visualize. So what we want to do is simplify the description and we're just going to keep track of the location of the ends of the string. Now, actually, I'm only going to keep track of one end of the string, and it's matter of convention whether I focus on the right-hand end or the left-hand end, but I'm just going to track, say, the right hand so that choice will force some asymmetry into the description, but it's just an asymmetry of convention. And if I had chosen instead the left-hand end of the string, then everything would be flipped. So in particular, I'm ignoring the internal composition of the string. So to simplify things in this way, what I want to do is define a probability for the right-hand end of the string to be at a particular site, let's say site K, and so this probability, which carries a label K for the site I've chosen, and which will of course vary with time, is simply a restricted sum over these strings, and I'm just summing over strings with the right end at site K, and in that sum I take these amplitudes, which as I said are real, so I simply take their square. Now, it was important that, at least initially, these strings had a conserved density. And if this is a conserved probability in some sense, then I'd like to be able to see that. But I can, it's rather straightforward. What we have is that if I sum over k, pk of t, then I'm summing over the different locations for the ends of the string. So what I do is go from this restricted sum over strings to an unrestricted sum over strings of a squared t of s, but this I already decided was equal to 1. So these probabilities for the string to end at site k, since the right-hand end of the site must be on one of the sites, those probabilities must add up to 1. Okay, is that all clear? So now our objective is to study the evolution with t of pk of t, and basically I'm going to draw some pictures and make some arguments, and those pictures need some notation. So I need to discuss what's going on at different sites. So the notation is defined site by site. So in these three pictures, I'm just thinking about a single site. And one possibility is that in the operator I'm thinking about, I have the identity. And another possibility is that I have a non-trivial operator so one of the q squared minus 1 operators that's orthogonal to the identity. And at some other times, I'll just want to record the site without making any commitment to what operator is acting there. So I need some notation for that, and that's a circle with a cross through it. So this is any operator. Okay. So now we want to think what happens in one half time step of this random quantum circuit. So I say half time step because in alternate half time steps, if I use what's called the brickwork geometry that I've been drawing, then in 1/2 time step we have unitary gates acting between nearest neighbor pairs of sites on, say, the even bonds, and in the other 1/2 time step we have gates acting on the odd bonds. So I'll think about a pair of operators, and what happens when I evolve with a gate coupling the two sites. So I want to talk about this sort of evolution. And at the moment, I might have any operator there, and this would be a two-site unitary gate, and this would be its conjugate. And then if I think more specifically about what I might be interested in considering here, then one possibility is that the string ends at the left side of this pair, which I'd represent by saying that there's the identity operator on the right side, and in order that the end of the string is on the left side, there must be some non-trivial operator acting there. And the other possibility, if this is close to the end of the string, is that the string ends at the right side, in which case I must have a non-trivial operator there. And on the left side, in that case, well, that's somewhere in the interior of the string, so I don't care what kind of operator I have there. It could be the identity, it could be something non-trivial, so I simply represent it like that. So this is a string ends at the right side. And those are the two cases for which I really need to consider time evolution, because if I'm not dealing with one of those two cases, then I'm not considering what happens at the end of the string, and it's the evolution of the end of the string that I need to understand to talk about the evolution of pk with t. So are the ideas there clear? Any questions? Yes?
Sorry, just like to clarify notation. This A of S is not the same as A sub S of T that we have in our definition.
Oh, sorry, did I? Yeah, sure. Thank you for that. Let me correct it. Thanks. Okay, so now we need to think what can happen under time evolution in these two cases, and I'm going to get shorter space, so let me draw them like this and like that, and okay, so one possibility, which in general will have some weight under this evolution, is that after we've acted on this pair of operators with u on one side and u dagger on the other, we get some contribution to the overall amplitude, which corresponds to the string advancing. So if the string advances, that means we have a non-trivial operator on the right side, and in that case, we no longer care what's on the left side. So this is the string advances, and by elimination, the other possibility is that the string is unchanged. And in that case, we have a contribution to the overall amplitude in which we still have the identity here, and we have something non-trivial at that site. And in this case, well, things are a bit asymmetrical. So one possibility is that the string remains in the same place, in which case we have a non-trivial operator still at the right and whatever we like on the left side. But now the other possibility is that the string actually retreats, and it'll retreat if we wind up with an identity operator on the right, and then something non-trivial here. Okay, so yes. Yeah, but the idea is that we don't care what's in the interior of the string. So one possibility is that the string advances and we have a non-trivial operator here and also a non-trivial operator on that side. But another possibility is that the string advances, we still have, we must then have a non-trivial operator here, and we could have the identity there. But there's no point in distinguishing between the two because we're just trying to take this very coarse-grained view of the dynamics where we follow the location of the string end, but we don't take any account of what's going on in the interior of the string. I mean, in principle, it would be interesting to think about the interior of the string, but it makes it more complicated. You mean the left-hand end of the string? Yeah, okay. I'm really imagining now that the time evolution has gone on for long enough that the right and left ends of the string are well separated, and it's okay just to think about the right end. I mean, actually, there's no approximation there, but to not get worried about the left end, we're just focusing on the right end. Okay. Now, at this stage, you might want to sort of check that this all makes sense, and we've covered all possibilities. So, for instance, taking these top two alternatives, which come if the string initially ends on the left side, we've allowed for both possibilities on the right-hand side, we've allowed for the identity or some non-trivial operator. But one thing, in fact, the only thing that hasn't been included is evolution to an identity at both sites. So we've excluded identity times identity. And there's a good reason for that, because in this case, if I go back to equations, I'm saying we have some non-trivial operator on the left side and the identity on the right, and we're evolving it with U and U dagger. And the question is now whether I could get identity times identity, which is the case that I'm excluding. And clearly I can't, because if I rearrange this equation, then I can multiply from the left by U and from the right by U dagger. And that's, of course, equal to identity times identity. So since I excluded an identity on both sides by assuming that initially I have a string ending at one of these two sites, I can't generate identity times identity as the final operator. Okay? So now we'd like to associate some weight with these possibilities, and let me give it a name and then talk about how to calculate it. So these are probabilities, and they're probabilities that come, well, from averaging over different choices of gates. So one way to work out these probabilities is to use the information on averages over unitary matrices and Weingarten functions, which we heard about earlier, and actually one of my problems guides you to doing that. But in the lecture, I'd like to try and take a shortcut, and actually I realized that I've got probably to the full hour, so maybe we should have a break, and then I'll talk about the argument that gives you a value for these probabilities P. Okay, thanks. Okay. So when we stopped, we got to this point where we were thinking about two possible situations for the location of the end of the string in relation to the next application of gates in the random unitary circuit, and then these various possible outcomes of the evolution. And what we want to do is work out these probabilities, which are the weights for the probability of the location of the string to evolve as these pictures show. So there's a microscopic way of calculating what these weights are, and in the microscopic approach, you'd first of all start with one of the situations, which is represented here. So a particular non-trivial operator on the left side, the identity on the right side, and you'd evolve it with U and U dagger, and then you'd work out the amplitudes to get one of these outcomes here, and then to go to the probability that we're trying to track, you'd convert those amplitudes into probabilities, and you would average that calculation over choices for the unitary matrix representing the gate using the Haar measure. And that's not hard to do, and I hope you'll do the problem in the problem set that I suggested to see how the calculation goes. But for the lecture, we want something a bit simpler. So this is the shortcut to finding P, and basically we want to count possibilities and think, and the assumption we'll make is that if we use the Haar measure for U, then the different possibilities have equally probable outcomes, and so just by counting the possibilities, we can work out what P is. So if we think about the ways to advance, and sorry, I should have said I'm going to think first of all about the first case, which is the string end on the left side. Then the ways that we can advance, well, we have any operator on the left side after the action of U and U dagger, and we've already said that there are Q squared possible operators in the basis. So Q squared is the number of operators on the left side. But on the right side, we've said that there's definitely a non-trivial operator in order that we're dealing with the case where the string end has advanced, and there are only Q squared minus 1 non-trivial operators. So this is the number of operators on the right side. And then the complete number of outcomes well, it's all possible operators on this pair of sites, excluding the identity, which, as I explained, we can't evolve to. So we have Q squared operators on a single site. So on a pair of sites, we have Q to the 4th operators, and then we exclude the identity. So we have Q to the 4th minus 1. So if we make this assumption in our shortcut to finding P, then P is the ratio of these two numbers. It's Q squared times Q squared minus 1 over Q to the 4th minus 1. So we can cancel that down to q squared over q squared plus 1. And then this number is the complement necessarily, but if you ran the same counting argument, you'd find it automatically. And I don't want to repeat that in the other case, but of course, you can go through things, and what you'll find is that you have P for the upper possibility and 1 minus P for the lower possibility. So the picture that we've got is if we have a string ending on a particular site, then according to whether we're dealing with an even or an odd half time step, we'll have gates acting either between this pair of sites or between that pair of sites. So, yes. No, there's absolutely not time reversal symmetry. I mean, the time reversal symmetry gets lost when we go to probabilities. So the probabilities are written the way they should be, I think, and we can calculate things but you can kind of see that it must be the same because at the level of the calculation I gave, I just counted the number of operators which are included here. And since this is the same picture, the number of operators that are included must be the same. And so there's, yeah, so the string advances with some probability P, and in this case, it stays where it is with probability 1 minus P, but then there's some asymmetry introduced by the choice of the initial situation. And if this is the initial situation, then what happens is it stays the same with probability P and it retreats with probability 1 minus P. And that asymmetry is absolutely crucial, as I'm about to say, or in fact, I was in the process of saying. So in an even half time step, where we're dealing, say, with this top situation, then the end of the string remains or jumps with probabilities 1 minus P and P, and in the odd half time step, where the gates act on the other pair of sites, a string which is initially on the ending on the middle site will remain where it is with probability P and jump back with probability 1 minus P. So if we want to think about the dynamics of the length of the string, we can define the average end of the position of the string which is just the sum of these probabilities for the string to end on a particular site k, weighted with k. And then, well, if you analyze this stochastic process in more detail, and I'm not going to go through all of that because some of it gets a bit messy, but what you find, and what I think is reasonably obvious, is that x of t grows with linearly in time, and this velocity is just what you'd think from combining these two pictures. So so in the first half time step, the change in the position is +1 with probability p, or 0 with the complementary probability. And in the other half time step, the change in the position is 0 with probability p, and -1 with probability 1 minus p. So the velocity is 2p minus 1. And that is q squared minus 1 over q squared plus 1. And for all choices of this local Hilbert space dimension, which of course should be an integer equal to 2 or bigger, this is bigger than 0. And that's exactly the kind of asymmetry, I think, which was bothering you. And it's that asymmetry which is kind of central to this process. Questions? Thanks. No, in this picture, I'm assuming a brickwork architecture so that the gates in what I'm calling half time steps are alternately on even bonds and odd bonds. Yeah, that's true. And I mean, basically, by this point, once you've evaluated these P's, you're dealing with something that's equivalent to a classical stochastic process, a rather simple one, but it's got an irritating feature that there are two sites in the unit cell, and the time evolution has got these two half steps. So if you want to follow it in full detail, then you have to take account of those features, which of course you can do in pretty elementary ways. But I don't want to get drawn into those kinds of details. But I hope that it's plausible to you that there's a velocity, and the key thing is that the velocity is positive because of this asymmetry that I've been talking about. Any other questions? Yes. Right. So now we've summed over all strings. So first of all, we've gone from amplitudes to probabilities by taking the squares of the amplitudes for the different strings, and we've summed over all strings that end at a particular site, and then when I work out this average position of the string end, I've summed over all possible sites. And what's more, I've also averaged over different realizations of the circuit. So we've got a long way from the individual strings, but the claim is that we're retaining the bit of information that's interesting. Yes. Well, I'm simply trying to summarize here what's on this board. So what I'm calling an even half time step is this first possibility, and an odd half time step is this second possibility, because if I'm taking the gates to act here in the one case and there in the other case. Yeah, I agree it's not obvious, but it's not completely obvious, but when you think about the arguments that I made, I hope that you'll see that it does turn out to be P in both cases, not P and P primed. So the point was that the argument involved counting the number of operators that correspond to this picture. And when we run the argument again down here, because we've got the same picture, the counting is just the same. Any other? Yeah. Thank you. Yeah, that was exactly something I wanted to say, but might have forgotten. So if we take Q to be 2, or in fact any finite value, then this velocity is less than 1. And of course, there's some question about units, but if you're careful with the units, then a velocity less than 1 means that the operator is spreading less rapidly than the trivial geometrical light cone which I drew earlier on. But on the other hand, if you take the limit q goes to infinity, then this trivial geometrical light cone is the physical one as well. Yeah, so okay, so the other points I want to make will be more qualitative. What we want to do is summarize what the evolution of pk of t, and we can draw pictures of p of k as a function of k at different times. So suppose the operator that we started with at time 0 was located here, then sorry, let me take it to be at the origin of this graph. Then at some short time, the probability distribution might look like that, and at some longer time, we might have a picture like that. And this distance then should be v times t2 minus t1. And I'm drawing the probability distribution for the end of the string at each time as something with a certain width. And the reason you should expect that is that the string doesn't necessarily advance or stay where it is. It can even move backwards. And in fact, you get diffusion. So this width is some diffusion constant times time square root. And you can work out the diffusion constant, but it takes a bit more time. What you find is that this diffusion constant is 2q squared over q squared plus 1 all squared. So for finite q, you have a finite diffusion constant, but if you take q to infinity, then d goes to 0. Yes?
How do I interpret that graph? Because I think we have k as the x-axis, so you're labeling.
Right. Well, I've put the labels on in an asymmetrical way, but in fact, P depends on two arguments, K and T. So remember, P is meant to be the probability that a string ends at site K at time T, and now I'm plotting that. I'm fixing T. Yeah. Yes. Well, we do have a conserved quantity because we saw that the probability density over possible strings is conserved. I mean, it's an important point, but the answer is that it is a conserved quantity. Okay, so there's one more point to make here, which is to connect this back to the OTOC or the behavior of the commutator. So far we've seen that it's right to imagine that an operator initially located, say, at a single site will grow over time into a superposition of many strings. And what we've learned is that the average length of these strings grows with a velocity which maybe I've rubbed off, but which I had on the board. But what about actually thinking about the OTOC? So what we want is and what we've done so far is written Ox of t as a superposition of strings with amplitudes. And what we know now is something about how these amplitudes behave. So what we want to do is think about putting this expansion into the commutator and so on. And let's take q equals 2 for simplicity. And I'll take OY. Now remember, Y is a site label, so I'll take it to be the Pauli Z at that site, and identities everywhere else. And so when I think about what the commutator is with a particular string, then what I need to think about is what the operator in the string is that acts at site Y. And if I think about the possibilities, then I could have the identity at site Y, or I could have X at site Y, or the operator Y at site Y, or the Pauli Z operator at site Y. And so the corresponding commutators squared will be zero in some cases and proportional to the, well, so if I take 1 at site Y or Z at site Y, then the commutator squared averaged will give me 0. And if I take X at site Y or Y at site Y, then because these give me another Pauli when I commute with the Z, well, in fact, it gives me 2 times a factor of I times a Pauli, then, well, in this case, I have so this will give me 4, and likewise 4. So what this means is, well, it's not obvious, but it's at least plausible, I hope, that if the end of the string is past the point Y, then each of these 4 possibilities are equally likely. And so we can average over them with equal weight, and then what you find is that the value of this commutator is, well, averaging over these four possibilities, we get 2 from 2 zeros and 2 fours. And we get contributions like this if the string end is to the right of the site y, and if the string end is to the left of the site y, then we definitely have an identity operator here, and so we get a contribution 0. So this commutator is the sum of pk of t with k greater than or equal to y. Is that understandable? Yeah. Yes. No, because we're taking all of these gates to be hard distributed unitaries and we're averaging over them. So even after one time step, we lose any information once we've averaged on what the initial operator was, because a unitary can rotate a specific choice of that operator into any of the alternatives. So I shouldn't have rubbed off those pictures, but I had a picture as a function for pk as a function of k, which did something like that. So if I take a particular value of y, then in this instance, I'll have cx minus y t at t1. It'll be small because when I sum like this, I'm just summing some small tail. But on the other hand, at t2, the weight of this probability distribution is almost all to the right of the point y. So I have a value up here. And now, once we know that the width here broadens diffusively, we know that this is diffusive in width. So if I plotted things at a fixed time as a function of the separation, I would have a width that was proportional to the square root of time. Okay. What do you recommend I do? I mean, I started a bit late, but on the other hand, we're 1:05. I can. Yeah. Okay. So the next thing I want to talk about is entanglement spreading, and the first thing is to remind you of some basics about density matrices. Well, first of all, can I check? Do people generally feel they know what I'm talking about if I talk about a density matrix? Who Right. Okay. And what about entropies? If I talk about Renyi entropies, is that familiar? No. Right. Okay. So let me pretty fast just define Renyi entropies and maybe a few other basic things, and then hopefully you'll be equipped for what I want to talk about tomorrow, which is entanglement spreading. So if I start off with density matrices, just to define some notation, then I want to talk about rho, which is written in that way with these n being a complete, well, orthonormal basis, and the PNs being real and normalized. And then we can talk about entropies. So we have the von Neumann entropy in the usual way as being sum over n of minus Pn log Pn. And essentially for calculational convenience, we also would like to talk about Renyi entropies, which are right as S alpha. And if we define them via an exponential, then you can see why they're convenient things to talk about, because they're traces of powers of the density matrix. And in particular, what we'll discuss partly tomorrow is the purity, which is simply this exponential for the case where alpha is equal to 2, so the trace of the square of the density matrix. And I guess one other thing that's worth knowing is that the von Neumann entropy is the limit as alpha goes to 1 of these Renyi entropies, which you can amuse yourself by showing. And then we need to perhaps remember what these quantities tell us. Well, obviously they tell us something about the distribution of probabilities. So if we have a pure state, then we have 1 Pn is equal to 1, and that implies that all the others must be 0. And then all the S alphas for different values of alpha and the von Neumann entropy are 0, as you can check. And the other possibility that it's useful to keep in mind is what happens if we have a maximally mixed state. Meaning that the PNs are all equal, so I'll take them all to be 1 over n in an n-dimensional Hilbert space. And then, again, you can check this. What you find is that the entropies are all log n. And also the von Neumann entropy. Okay, any questions about that? So there's, how are we doing? Yeah, okay. So I just wanted to say a few things still on this elementary reminder about reduced density matrices. So suppose I have a system and I decide that I'm only going to make measurements in some part of it. So I'll call that A, and then the complement, that subsystem I will call B. And in order to work out the effect of doing measurements on subsystem A, it's enough to think about the reduced density matrix, which I'll write as rho sub A, which is simply a trace over the degrees of freedom in B of the full matrix. So can I check, is this familiar to everyone? Right, okay. So you can think, for example, of a pair of spinor halves and put them, for instance, in a singlet state and take the trace of trace over one of the two spins, and then what you find is that the remaining spin is in a mixed state with, in fact, maximal entropy. So is that kind of calculation familiar? Okay, so tomorrow when we talk about entropies, entanglement spreading, we'll think, for example, about a system which is initially in a product state, and we'll think about the effect of time evolution. So, for instance, time evolution might generate entanglement in the form of singlet pairs with one spin in the singlet pair in subsystem A and the other in system B, and then you might find that the entanglement that you calculate, or the entropy that you calculate from subsystem A at some later time would be the log 2 for a given singlet pair times the number of singlets between A and B. Okay, so that kind of picture is familiar for people. Anyone want more details? No. Okay, that's great. So I'll stop there, and we're kind of equipped for the things which I want to say in the lecture tomorrow. Thank you.